Welcome to online training session day 8 part 1 as the size optimization. I have divided size optimization into two parts, that is part 1 and part 2. I have divided some of the tutorials in part 1 and some of the tutorials in part 2. So let's see the training series details. We have covered day 1, day 2, day 3, day 4, day 5, day 6, day 7. Now we are on to the day 8, and as I have already mentioned that I have divided day 8 into two components, two parts as part 1 and part 2. So the topics which I am going to cover in this part, that is the first part, are 3D size optimization of rail joint, size optimization of welded bracket, composite bike frame optimization, discrete size optimization of a welded bracket, size optimization of shaded. So let's start with the first tutorial. So this tutorial demonstrates how to perform a size optimization on an automobile rail joint model with the shell elements. The structural model with loads and constraints applied is shown in the figure below. The deflection at the end of the tubular cross section cross member should be limited. The optimal solution would use a little material as possible. The structural model shows below is loaded into hypermesh. The constraints, load, material, properties and subcases are already defined in the model. Size optimization, size design variables and optimization parameters are defined, and OptiStruct is used to determine the optimal gauge for the component. The results are then viewed in Hyperview. The optimization problem for this tutorial is stated as: my objective of this particular optimization problem is to minimize the volume. My constraint, a given maximum nodal displacement at the loading grid point for the two loading conditions. My design variable are gauges of the two parts. In this tutorial, we will see how to set up a size optimization in Hypermesh, post-process the size optimization results in Hyperview. So let's open Hyperview, HyperWorks Student Edition. So go to Start, All Programs, HyperWorks Student Edition. You can open it from Start. Select the user profile as OptiStruct. If you are using HyperWorks version 11, select the user profile as Radios Bulk. But if you are using HyperWorks version 12, select the user profile as OptiStruct. Click OK. So it will load the required templates required to generate the deck for the OptiStruct solver. So it has loaded all the required templates. I'll just close this, maximize the window, and open the model. So open the model, click on the open folder, browse the location. This is my model. With the components, load collectors, load step, material and property, everything is predefined. So I will directly start creating the deck for optimization. So first step is to create the size design variable for our optimization. So to define that, I will go to analysis page. On analysis page, I will select optimization panel to enter to optimization panel. Then I will select size panel from the given list to define the design variable for the size optimization. I will enter the design variable name. Let's suppose I'll enter as tube. We'll enter the initial value as 1, lower bound as 0.1. Upper bound as 5. Then make sure the move limit toggle is set to move limit default, and make sure the discrete design variable, that is DDVAL toggle, is set to no discrete design variable, and click on create. So the design variable is created for tube. A design variable 2 has been created. The design variable has initial value 1, the lower bound as 0.1 and upper bound as 5. Now we will repeat the same step to define a different design variable for rail. With the initial value as 1, lower bound as 0.1 and upper bound as 0.5, and click on create. So this is the size variation limit. Initially the value will be 1, then the lower and maximum bounds I have defined. Then click on generic relationship. Enter the name of the generic relationship as tube underscore th. Click on the property and select tube 2 from the list of the property collectors. Make sure the toggle is set to the thickness T. Click design variables. Check the box next to tube. Note the linear factor value in the box beside the tube here automatically gets set to 1. Click return and click create. So a design variable to the property relationship tube th has been created relating the design variable tube to the thickness entry on the P-shell card of the property tube 2. Similarly, I will create another design variable relationship. Select the property as tube 1, design variable as rail, and create. So I have defined two design variable property relationship. Then click return to go back to the main menu. With this, I have defined the size optimization design variable. That these are the design variables and the property of the thickness variation it will take from the design variable property relationship. Now the next step is to define the responses. So as per my constraint and objective, I have to define two responses. So first I will click on the responses panel, enter the response name as volume, select the response type as volume from the list available. Make sure the total region is selected. Click create. Then enter the response as X displacement. Switch the toggle to static displacement. Enter the node number by ID as 3143. That is the node where the forces is applied. Select degree of freedom 1 and click create. Degree of freedom 1 stands for translation along x-axis. Then select Z displacement. Select the node by ID. Enter the same node number, that is 3143, or select that from the GUI. Select degree of freedom 3 and click create. So you can see my two design variable, two more responses for displacement X and Z has been created. So a response Z displacement is defined for the Z displacement of node number 3143 where the force is applied. Now I will apply the constraints on my model. So I will click return to go back to the optimization panel and click on D constraints. Just below the response panel you will find D constraints. Enter the constraint name as say displacement X. Enter the upper bound, check the box in front of upper bound and enter the value as 0.9. It should not go beyond 0.9. And the response type is X displacement. Select the load step as force X and click create. So my first constraint is defined. Similarly, I will create another displacement constraint for Z. For this, I will put the upper bound value as 0.6, which is as per my problem definition. Response as Z displacement, load step as force Z, and create. Then I will click return to go back to the optimization panel. Now the next step is to define the objective function of the size optimization problem. So in this, the objective is to minimize the volume response. So I will go to objective panel, which is on the third column, fourth row. My objective is to minimize volume and click create. So on the model browser, you can see your objective is now defined. Now I will save this file, click return and return, go back to the main menu. Now I will save this file, go to file, save as model, desktop, in the new folder, let's say tutorial 6, save. Go to analysis, OptiStruct, export option to all, run option to optimization. I will increase the memory size to say 1000 and click on OptiStruct. This will start the solver optimization. OptiStruct, it will initiate the solver as OptiStruct. So now my optimization is under the solution process. So my optimization has been converged and my feasible design with all constraints satisfied has been achieved. So I will click on results to view the size change of this particular model, that is the thickness variation. We will see the thickness variation for this model. So we have given the range from 0.1 to 5 with an initial value of 1. So we will see for the particular loading condition what will be the thickness variation. So we will move to the last iteration, elemental thickness, simple, and just click on apply. So the thickness value required for the optimization process will be like 1.59, that is 1.5 mm is good for this particular model, as you can see, which satisfy my constraints. So I'll see the constraints values for this. So I will open the model, that is tutorial number 6, S1 file, apply. I will split it into 4 or 3, let's say 3. And that is the subcase 1, force x1, x that is, and this is force z. So contour, apply, this is the displacement, contour and apply, this is the displacement for this. So static min max, maximum value, min max, maximum value. So as you can see, this is for the zeroth iteration. The value is coming as somewhat 1.5 and it's 1.9. But for the last iteration, my values are 1.6, which are my constraints, and 0.7, which are my constraints. So I have constrained it to the 0.9. It should not go beyond 0.9 and this should not go beyond 0.16. So I have achieved the target, which is the constraint which I have given with this thickness. So by varying the thickness, so initially my thickness I will check. So if I go to property and tube 2 and say update, my thickness is 0.8. So when I change the thickness to 1.5, I will achieve the desired displacement. So in this way you can vary the thickness as per your constraints and objective for your model. So in this way, I have ended with this tutorial. So I will close this. I'll also close this, click new, and move to the next tutorial. So the next tutorial is size optimization of welded bracket. So this tutorial demonstrates how to perform a size optimization on a welded bracket modeled with the shell element. The structural model with loads and constraints applied is shown in the figure below. The objective is to minimize the amount of material used in the model subject to certain stress specifications. The gauge changes of the bracket are linked to each other so that the gauge is identical for both sides at the optimal design. The structural model as shown in is loaded into hypermesh. The constraint, loads, material properties and subcases are already defined in the model. Size, design variable and optimization parameters are defined, and OptiStruct software is used to demonstrate the optimal gauge. The results are then viewed in hyperview. The optimization problem is stated as my objective is to minimize the volume. My constraints are maximum 1 Mises stress of the bracket should be less than 100 MPa. My design variable is gauges of the brackets. In this exercise, we will see the setup of the optimization problem for size optimization, submitting the job to OptiStruct and viewing the results by using hyperview. So again, we'll move to the HyperWorks 12 student edition. So let's open the model. So click on open folder, browse the file. So this is my file where the force is applied, constraints are also applied. The components, load collectors, load step, material property, everything is predefined, as you can see. So again, we will start directly with the defining of size optimization. So first step, again the same is to define the design variable. So to define the design variable, I will go to analysis page, optimization. Select the size panel. Select the radio button as DSVAR, that stands for design variable. Enter the design variable name as part 1. I will enter the initial value as 2.5. The lower bound as 1. And the upper bound will be 2.5. So I want the thickness variation is from 1 to 2.5. I'm giving the range, the lower and upper bound. Set the move limit toggle to move to default limit and no discrete design variable. Click create. Then I will create one more for the part 2. With the same initial value, lower bound and upper bound, click create. So I have defined 2 design variables. Now the next step is to define the generic relationship, that is the property related to that. So I will enter the name as part 1 thickness. Select entity selector switch. I will toggle it to properties. Select the property as part 1 and make sure the property selection switch is selected as thickness T. Design variable part 1. Click create. Similarly, I will create for part 2. Property will be part 2. Design variable will be part 2 and create. So a design variable to the property relationship part 1 underscore th has been created, relating the design variable part 1 to the thickness entry on the pre-shell card of the component. So we can check the thickness here. if I check the thickness for part 1, it's 2.5, that is the initial value. Similarly for the part 2, it's 2.5. So I want it to be lower than the actual value of the thickness. Now I will link the design variables. So I will click on design variable link, enter the design variable link, that is D-link as link 1. Under design variable, select part 2, dependent design variable, select part 2, and independent will select part 1. Set C0 value as 0 and C multi value as 1 and click create. So my design variable link has been created. So the design variable part 2 is now linearly dependent on the design variable part 1. I did this because the change in the thickness will be linearly dependent on both of the components. I want to linearly vary the thickness for both of the components. That's why I linked them. So my software will not individually solve them. Instead of that, it will linearly distribute the thickness variation on both of the components. Now my next step is to define the responses. So I'll go to response panel, enter the response name as volume, select the type as volume, keeping all the parameters as it is, click on create. So my optimization response has been created. Then I will create one more response as stress, select the response type as static stress, select the property of part 1. I will select the stress type and select von Mises for both the surfaces, that is the front and the rear both, and click create. So a response stress 1 is defined for von Mises stresses of the elements in the component of part 1. Then click response and enter stress 2. Select the property as part 2. Keeping all the parameters as it is, just click on create. I will rename it as stress 1. So stress 1 stands for the values for part 1 and stress 2 stands for the values of part 2. So I have defined the responses. Now the next step is to define the objective function. So my objective is to minimize the volume response, and then I will define the constraints for this optimization. So I will click on D constraints, enter the constraint name as stress 1, select response as stress 1, click on the load step and select the load step which is created earlier. Check the box in front of upper bound and enter the value as 100 and click on create. So with this, a constraint is defined on the response stress 1. The constraint is an upper bound with a value of 100. The constraint applies to the subcase step. Similarly, I will create one more constraint for stress 2 with a response as stress 2, load step will be same and upper bound will also be the same, and click create. So I have defined two constraints as what is my optimization problem is stating that it should be less than 100. So I have defined it for the two cases. Now I have completely defined the size optimization problem. So I will save this file. Let's enter tutorial number 7. Save. Go to analysis, OptiStruct, keeping all the parameters as it is, just click on OptiStruct. So my analysis has been done. So I will click on results to view the results in hyperview, that whether it has given the proper thickness values or not, or also whether it has given the proper stress values or not. So both the things will check. So I'll close the message log. We'll move to the third iteration, contour, elemental thickness, simple, and apply. So the thickness required to achieve this stress values are 1.8 for this particular model. So earlier the thickness is 2.5, but in the final stage the thickness is 1.86. That's what it requires. So we'll see the stress results now. I'll split it into two. S3D S1. Say apply. S1 is the file to get the stress and displacement values of the optimization problem. So elemental stress 2D, 1 mysis, simple, and apply. So if I check the static mean max, my maximum stress is coming as 88.67. For the 0th iteration, it is 54. So for this particular component, I am allowed to get some higher values of stresses. So, but I want to reduce the thickness of the component so that the cost of the component will get decreased. So by reducing the thickness, it will increase the stress, but my allowable stress is 100. So I am getting the stress lower than 100, which is 88, and thickness is changed drastically to 0.7 mm approximately, which is a big thing. So in this way, you can get a variable change in the thickness, that what thickness is required for what values. So as per the constraints or the objective, you can define the size optimization. So in this way, I have ended with this tutorial. So I will close the hyperview GUI. I'll click new. Now we'll move to the next tutorial, that is composite bike frame optimization. So in this tutorial, you will learn the steps required to perform a ply orientation optimization for a composite structure. The figure below illustrates the model that will be used for this exercise. My optimization problem for this tutorial is stated as, my objective is to minimize the volume. My constraint is the given maximum nodal displacement. My design variables are layers thickness. So in this tutorial, we will see how to set up the size optimization of a composite bike frame, post-process the results of composite size optimization in hyperview. So let's open hypermesh. We'll open the model. So click on open folder, browse the file where you have saved that file. This is the file on which we are going to see the composite optimization for the bike frame. So as we can see, my component, material and property is defined, but I haven't defined any load collector and load step. So there is no loading condition is applied on this model. So first I have to define the loading condition for this model and then apply the load step and then process for the optimization process. So to define load collectors, click on load collector icon. Enter the load collector name as crank. Select a color. With no card image, click create. Create another load collector as SPC. Define a different color and click create. So I have defined two load collectors, one is crank, one is SPC, as you can see. So I will click return and apply these load collectors. So first of all we will create forces. So I will go to analysis page, force panel, make the crank one as the current. Just right click on it and click on make current. So select this node and enter the magnitude as -100. The direction will be Z. Click create. Click reject. We need to create it the other side, the crank one. Say create. So this is the force. Now click return to go back to the analysis page, and we'll create one more as movement. So go to analysis page, movements, which is on the second column, 5th row. Select the node on the opposite side. Enter the magnitude as 100. Select the direction as x-axis and click create. So a movement will get created. So I have created a movement and a force on this structure. Now I will create the constraint. So click return to go back to the analysis page. Right click on SPC, make it current. Go to analysis constraints. And constraints this as well as this. And this one as well as this one. For all the 6 degrees of freedom. So I have constraints these for the 6 degrees of freedom. The degree of freedom 1, 2, 3 stands for translation along XYZ axis. Degree of freedom 4, 5, 6 stands for rotation about XYZ axis. Now I will define a load step for OptiStruct analysis, that is a static analysis case. So I'll click return to go back to the analysis page and click on load step on the same analysis page, which is on the 5th column, 3rd row. Enter the name of the load step as crank. Select the type as linear static. Check the box in front of SPC. Check the box in front of load. For the SPC, select SPC, and for load, select the crank. So an OptiStruct load step has been created with which reference the constraints in the load collector SPC and the force in the load collector crank. So click create. So in this way you can see my load step is created. Now I will start working with the size optimization for this bike frame. So now we will define the process for size optimization. So I'll go to analysis page optimization. But before that, we will go to 2D hyperlaminate to define the thickness variation for the composite lamination. Right click on design variable and click on new. So this will help us to create a new design variable for composite bike frames or composite material. Enter the name as thickness 1. Enter the initial value as 1. Enter lower bound as 0 and upper bound as 2 and click on apply. In the similar manner and with the identical values, we will create 4 more thickness as thickness 2, initial value 1, 0, 2. And say apply. Similarly, 1, 0, 2, apply. One, 0, 2, apply, and apply. So I have defined 5. So or alternatively, you can click on thickness 1 and choose duplicate from the floating menu to create an identical design variable. Repeat this for all the 5 and then rename. So you can also just right click on this, say duplicate, and rename the 1. So now we will click on PCOM branch to see all these different components, that is seat tube, top tube, down tube, chain stay, seat stay. So these are the different tubes. Click on the checkbox next to optimization. So a new field will appear. If you on this, a new field will get appear as which allows us to in the play layout table, allow the design variable to be associated to the ply thicknesses or ply orientation. So design variable, we can select the, so click on the field under design variable under optimization in row 1. Choose thickness 1 from the drop down. Similarly, the second one, thickness 2, thickness 3, thickness 4, thickness 5. Click update laminate. Click on update laminate. So this associates the design variable thickness 1, 2, 3 with the thickness of the ply of this laminate. In this case, these plies 2, since this is symmetric laminate. So repeat the same process for top tube, down tube using the same design variables. So for the top tube, check the box in front of optimization, design variable thickness 1, thickness 2, thickness 3, thickness 4, thickness 5. Scroll it down, click on update laminate. Similarly, down tube, optimization, thickness 1, thickness 2, thickness 3, thickness 4, thickness 5, update laminate. Go to files and exit. So with this we will exit the design variable. So 5 design variables and the respective property relationships are already will be created, as you can see. So for the down tube, top tube and seat tube, it will create the respective design variable property relationships and design variables. Now, as my design variables are defined for this composite laminate, now the next step is to define or create the responses. So I'll go to analysis page, optimization, and click on responses. Enter the response name as displacement. Select the type as static displacement. Select total displacement radio button. And select the nodes where the forces are applied or the loadings are applied. So these are the 2 nodes where we have applied the forces. And click on create. Then again enter the response type as volume. Select the response type as volume and just click on create. So the 2 optimization responses has been defined as displacement and volume. Now click return to go back to the optimization panel, and the next step is to define the constraints. So click on constraints and enter the displacement name of the constraint as displacement. Response type as displacement, load step as crank. Check the box in front of upper bound and enter the value as 1.8. I don't want the displacement to be more than 1.8. Click create. So a constraint is defined on the response displacement. It states that any solution with a minimizing the volume need to have a displacement lower than 1.8 mm will be feasible. Then click return to go back to the main optimization panel and define the objective. So click on objective. My objective is to minimize the volume. So I have defined the objective as you can see on the model browser. So I will click return. Again click return to go back to the main menu. So now I will save this file as I have defined everything. So I will save this file as say tutorial 8. Go to analysis, OptiStruct and solve the window. Click on OptiStruct to start the solver. So this will start the solver for the optimization process. So now my analysis has been completed. So I will click on results and close the solver window to view the results in Hyperview. So for the last iteration, the thickness variation will be somewhat like this. So from 1 to 3. So the portions which are in this is 1, as you can see. Some are in different, some are different. Also you can see here so the report summary. So these are these values. Also I will let's say split the window into 2 and open a session file here. So this is iteration versus values. So in this way you can view the results of the displacement plot, the elemental plots, all these things with the help of hyperview and hypergraph. So in this way I have ended with this tutorial. So I'll click new and move to the next tutorial, in which I am going to discuss about the discrete size optimization of a welded bracket. So this tutorial demonstrates how to perform a size optimization on a welded bracket modeled with the shell elements using discrete design variable, that is DDVAL card. So the structural model with loads and constraints applied is shown in figure below. The objective is to minimize the amount of material used in the model subject to certain stress specification. The structural model as shown in the figure is loaded into hypermesh. The constraints, load, material properties and subcases are already defined in the model. Size, design variable and optimization parameters are defined, and OptiStruct is used to determine the optimal gauges. The results are then reviewed in hyperview. The optimization problem is stated as: my objective is to minimize the volume. My constraint is maximum von Mises stress of the bracket should be less than 120 MPa, and my design variables are the gauges of the bracket. So in this tutorial we'll see how to set up an optimization or size optimization with discrete design variable in hypermesh, post-process the results in hyperview. So I'll open the model in HyperWorks Student Edition version 12. So this is the model, which is same as the previous one, where I have defined the component, load collector, load step, material property. Everything is predefined. We'll directly start with setting up the size optimization with discrete design variable in hypermesh. So go to analysis page, optimization, and click on discrete DVS, that is discrete design variable panel. Enter the name as DDV1. Click on the field next to form, from, and enter 0.5. With the same method, enter 2 to 3 and increment as 0.1 and click create. So my discrete design variable card is defined. So this setups a discrete design variable with a starting value of 0.5 and the ending value of 0.3. The variables are incremented by 0.1, making possible values as 0.5, 0.6, 0.7 and so on till 3.0. Now create another discrete design variable as discrete design variable 2 with all these data same and click create. Then click return to go back to the optimization panel. Then select size panel. Make sure the design DSVAR radio button is selected. Enter the DSVAR as part 1. Enter the initial value as 0.25, lower bound as 0.5 and upper bound as 3. With no DDVAL, toggle it to DDVAL and select discrete design variable 1. Click create. So a design variable part 1 has been created. The design variable has an initial value of 0.25 and a lower bound of 0.5 and upper bound of 3 and is linked with the discrete design variable of the name DDV1. Similarly, create one more design variable for part 2 with the same properties and giving the discrete design variable 2 and click create. So I have defined two design variables with discrete design value. Then click on generic relationship. Enter the name as part1 underscore thickness. Select the property as part1, design variable as part1, and click create. Similarly, for the part 2, select part 2 and select the part 2 as the design variable and click create. So I have defined design variable property relationship for both the things. So a design variable to the property relationship has been created relating the design variable to the thickness entry on the P-shell card on the component part 1 as well as part 2. Now the next step is to define the responses as per my constraints and objectives. So I will click return to go back to the optimization panel and click on responses. I will enter the response name as volume and click create. So my first response is created as volume. My second response as stress 1. Select static stress as the type. Click on the property and select part 1. For the von Mises stress and both the surfaces, click create. In the same way, create for second response, second property, von Mises stress, both surfaces, click create and return. Now I will create the constraints for this. So I will click on the constraint panel, enter the constraint name as stress 1, response type stress 1, load step as step, upper bound value as 120. Which is my problem definition. Click create, or for this one, for the stress 1, I will put it as 100. Similarly, enter the value as stress 2, take it 120, response type as stress 2, load step will be the same and click create. So I have defined two constraints for this model. So a constraint is defined for the response that is stress 1 or stress 2. The constraint is upper bound with a value of 100 and 120. The constraint applies to the subcase step, both the subcases. For both the constraints are for the subcase step. Then I will define the objective. So I will click on click return and go back to objective panel. My objective is to minimize the volume and click create. So in this way I have defined everything regarding to solve the model in using for the OptiStruct. I will click return twice to go back to the analysis page or the main menu. I will save this file. Save it. Go to analysis page OptiStruct and click on OptiStruct. So this will start the solver window. So my analysis is completed. So I will click on results to view the results of the thickness variation because of discrete design variable. So I will close this, select the last iteration, elemental thickness, apply. I'll use simple method to get the elemental thickness. So For this part, I want the thickness to be 1.8. For the other, I want the thickness to be 1.7 to get the required values. So let's see the stress values. So open this file, say apply, contour, elemental stresses, simple, and apply. So if I on the static values, so it's coming as 102, which is less than. So this is the upper part. So this for this it has to be 10 less than 120. So it is giving less than 120 for the thickness of 1.8. So initially this thickness is 2.5. So I have reduced it to 1.7 and 1.8 because for 1.7 I want the value to be less than 100. So in this way you can achieve the target required by your manufacturing or as per your requirement, that the stress values or the constraint, and change the thickness of the shell components. So you can get a desired thickness, that how much thickness is required to achieve that particular target. So in this way I have ended with this tutorial. I'll click new and move to the next tutorial. So now we will start with the size optimization of shoulder. So a size optimization is performed in this tutorial using OptiStruct. Size optimization involves the changing of the properties of either 1D or 2D or 3D elements, or 2D elements, not the 3D. These properties include area, moment of inertia of 1D elements, and the thickness of 2D elements. Size optimization is performed when it is not necessary to remove material, generate bead patterns, or change the shape of the structure. With size optimization, the cross-sectional properties of the element are changed to meet the necessary objective. Properties are linked with a design variable, that is DSVAR, using DVP REL card, that is design variable property relation card. This tutorial goes through the step involved in the defining size optimization for a model comprised of a shell and bar element. You will update the P bar L property to simulate the properties of the bar element and then link that to the design variable. The resulting design variable will have the higher frequency and updated element properties. In this, we will also use OptiStruct macros under a OptiStruct user profile to set up the optimization problem. So the problem statement is to minimize the global mass. My constraint is to transfer modes higher than 6 Hz. My design variables are beam width, beam thickness, beam depth, and shell thickness. So in this tutorial, we will see how to perform a finite element analysis and check the results. Define a size optimization with 1D element property. Post-process the optimization results. So I will open the model in HyperWorks Student Edition. I think this is an FEM file, so I will open this in, you import the file. And click on import. Click close. So you can see this is my model with shell and bar elements. So if I check the 3D representation, so you can see the C-section bar elements are being created. You can see here. So we will also change the dimensions of them. So initially we will save this file first and just run the basically run this model. Let's enter as tutorial 10 and see the results of the different modes. So this has been solved, so I will open it in Hyperview. So I will on the animation and increase the deformed value. Go to contour and say apply. We'll lower the speed. So this is the mode 1. For mode 2, mode 3, mode 4, 5, 6, 7, 8, 9, 10. So these are the different modes. So as you can see, the third and fourth mode are having the frequencies as 3.9 and 4.8 Hertz, somewhere around. So we will use that shape changes. This is more useful for us, and use them to see how the performance goes. So let's start with defining the design variable and beam cross section property. So first we will define the design variable using size panel. So we'll go to click return, go to analysis page optimization, click on size, enter the DSVAR radio button, that is design variable. Enter the design variable name as cover thickness. Enter the initial values as 3, lower bound as 1 and upper bound as 6. From this, select node discrete design variable and click create. Similarly, create 4 more design variables as beam wide, initial values as 50, lower bound as 30, upper bound as 90. Create. Beam height, initially as 100, lower as 80, upper as 125. Beam thickness 1, initial as 10, lower as 5, upper as 15. Create. And beam thickness 2, initial as 20, lower as 15, upper as 30. And create. Then assign cover thickness to the design variable. Then we will click on generic relationship, enter the name as cover thickness, click on the property and click on cover, select the design variable as cover thickness and click on create. Then define the property relationship for the beam dimension. The dimensions are defined as shown in the below point. So in this, each of the dimension of the C beam will be defined as the design variable. So enter dimension 1, select frame 2, property as dimension 1, design variable as beam width, click create, name as BIM2, property will be same as frame 2, toggle the property to dimension 2, and select beam height. Enter the name as dimension 3, property as frame 2, dimension 3rd, design variable beam thickness, create. Dimension 4, property as frame 2, dimension 4, design variable as beam thickness, and create. So I've defined 4 different dimensions of the C section. So I will show you what are these. I will take any one of the element. So if this is the element, then I will show you the what are dimension 1, 2, 3, 4. So dimension 4 is this thickness. Then dimension 3 is this thickness. The dimension 1 is this length, this thickness, sorry, this length of the element, and dimension 2 is this, the length along this side. So it will vary from this end, the thickness, and this thickness. So I have divided into 4 values. We can see the initial values. So go to 1D, hyperbeam, or you can go to property, frame 2, select the beam section values. Go to hyperbeam GUI. So this is dimension 1, as I have said it. This is dimension 2. The thickness is dimension 4. This thickness is dimension 3. So it's initially is dimension 1 is 50. This is 100. This thickness is 10, and this one is 20. That's what I have given, and given a range of the dimensions, so that my 1D properties will also get changed as per the requirement. Okay. So I will make it in a traditional mode. So in this way I have defined the design variables, the different design variables. Then we will define the responses. So go to analysis, optimization, and response. My first response is mass. Select the response type as mass. Click create. And my second response will be the third frequency, which I will try to increase. Select the response type as frequency, and the number of mode will be 3. Click create. Similarly, I will create one more as 4 for the fourth one, and say create. Now I will define the constraints. So I will go to deconstraint panel. Click on the constraint, name as constraint for F3. My lower bound is it should not go below 6. It should be higher than the value of 6. As earlier we have seen that it is somewhere around 3.8. So I want the higher frequency for this component. Similarly, for the fourth frequency, again I want the same thing, that I want the frequency to be higher than 6 Hz. And lastly, my objective is to minimize the mass. So in this way I have defined the optimization problem. So I will save this file. Go to analysis, run option to optimization, and click on OptiStruct to start the optimization process. So as you can see, my analysis has been completed. So I'll click on results to view the results of change of the frequencies of third and fourth. And also we'll see the dimensions, change in the dimensions. So I will open this shader.property file. Open with a notepad. So here you can see the changes in the values. So from the initial values, the values has been changed to these. And this is the design change. I will split the window into two. Open the H3D1 file, S1 file to see the fourth iteration. So now you can see my third and fourth is higher than 6. So by changing the thickness value, by lowering the thickness value of the shell elements, so here if I click to the elemental thickness for the fourth iteration, you can see the thickness value is changed to somewhat little. Or if I only see the thickness values of these, so these are the values. So in this way you can also vary the thickness of 1D elements as well as 2D elements both, and also change the cross-sectional thickness of the components. So in this way I have ended with this tutorial. Thank you very much for attending this session. If you have any points related to improve the online training session, please help us by sharing your valuable comments at edu-support@india.altera.com. If you find something interesting on this, then also please share your comments with us on edu-support@india.altera.com. Your comments will definitely encourage us to provide more this type of videos regarding the analysis and other related stuff. Thank you very much.